Okay, so this video talks about one of the last things in section 2.2 dealing with Hamilton circuits, or also known as Hamiltonian cycles. Specifically, we're going to look at gray codes. Now, gray codes are a very specific term for a very specific item, and we'll define what that is here in just a second. But it is an application of, or a type of, if you will, Hamilton circuit or Hamiltonian cycle. Okay, so first we need a little bit of background, and that's dealing with binary numbers. Okay, so if we convert numbers into binary, and I'm just going to look at binary strings of length 3. Okay, so if we look at length, oops, I do not want that to be blue. So length 3 binary strings. Okay. Now, to remind ourselves in terms of when you're writing binary numbers, they have placeholders just like any other number. The one that is the rightmost guy deals with the position that represents 2 to the 0, and then it's the guy that represents 2 to the 1, then the one that's 2 squared, then the one that's 2 cubed, and I realize this I need to replace that 3 with a n because the next one would be 2 to the 4th, and it keeps going. Okay, so let's go ahead and erase this 3, and we'll actually be specific to 3 in a second, but this would be length n binary strings. So a little bitty baby example, and I am assuming that most of you have worked with binary numbers before, but if not, here's a little bitty baby example. Maybe you have something like 1 1 0 1 0. So in this particular guy, this is exactly the same thing as, let's see, there's 5 of them there. So this first one would be 1 times 2 to the, let's check it out, 0 power, first power, second power, third power, fourth power, plus 1 times 2 cubed, plus 3 times 2 squared, plus 1 times 2 to the first, plus 0 times 2 to the 0 power. So this is the constant term. In base 10, this would be like the tens digit. In our case, it's the digit that corresponds to 2. So this one, the digit that corresponds to 4 or 2 squared, the digit that corresponds to 8 or 2 cubed, etc. Okay, so if we then figured out what this number actually equaled in base 10, you're looking at 2 to the 4th, which is what, 16, plus 2 cubed, which is 8, plus 0, which doesn't exist, plus 2, plus 0. Okay, 0 exists. You need it. It's a placeholder. But if you add all these together, the 2 and the 8 form 10, so this is 26 in binary. Okay, so just to remind ourselves. Now, specifically, if we look at our length 3 guys, let's write out all the length 3 binary numbers. Okay, well, you've got 0, 0, 0, 0, 0, 0. So that's exactly the same in base 10 as 0. If you look at 0, 0, 1, that's the exact same as 1. If you wanted 2 in binary, well, the 2 is the second position, so that's 0, 1, 0. The 3 would be what? 3 is the same as 2 plus 1, so that would be 0, 1, 1. So there's the 2 plus the 1. If you wanted 4, well, 4 is 1, 0, 0, because notice the 4 right there. 5 is 4 plus 1, so 1, 0, 1. 6, that's not a 6. 6 is 4 plus 2, so that's 4, that's 2, that's 0. And 7 is 4 plus 2 plus 1. Okay. Now notice when you're reading down these binary strings, what happens? And I'm going to go ahead and highlight this so it's easy to see. When you go from 0 to 1, only one digit changed. When you went, though, from 1 to 2, we actually had 2 digits that changed. When we went from 2 to 3, we had only one digit that changed. When you went from 3 to 4 here, we actually had all of the digits changed. And one of the things that people have looked at for years and years, ever since some of the very first counting machines back with Babbage, what they looked at is something known as a gray code, Honestly, gray code is named after a guy whose last name was Gray. But they were looking at these things of when they were implementing it with computers, and we do it also with not with respect to computers, but they were looking at it where they could order these binary strings so that only one of the digits changed at a time. And part of that was so when they implement it into these um, older original computers, they only had one mechanism changing at a time. Okay? Terms of why it's used now, I mean, you've got some different reasons because the actual machines are different, but that would be some of the original reasons to use gray codes. But at the end of the day, this is the definition of a gray code. Okay, so let's actually put this in the green that we normally use for definition. So definition of a gray code. All right, so here's the definition, and it is, well, this is specifically the definition as applied to binary strings, okay? Because gray codes you can actually apply to things that aren't binary strings too. So what you have is you have a list of certain objects. If they're binary strings, they're binary strings. You typically will have the list of all of the objects of a specific type, although it can technically be shorter as well. So you have a list of length, whatever the length is. If you deal with binary strings, you're going to write those binary strings in such a way that the next string in the list is going to differ from the previous string in the list by exactly one character or one digit. So for example, when we wrote out the first all 8 binary strings of length 3 up here just above, 0 to 1 was perfectly fine because the last digit here was the only one that changed. This 0 changed to a 1, but listing the number that correspond to the base 10 2 after the base 10 1 didn't work because we actually had 2 changes. So this guy would not be an example of a gray code. You can also have gray codes of other things. I've worked with gray codes on permutations, and permutations, you define the thing that differs by one move or one fill in your blank. The key thing with the gray code is it's a list of objects, and the consecutive objects in that finite sequence or that list, they have to differ by one, and then you define what that one thing is. For binary strings, it's one of the digits change, and that's it. So let us look at an example. Okay, and specifically, I'm going to still look at the length 3 binary strings, and what we're going to do is we're actually going to change the order of these guys. Okay, so let us do red for an example, since that's what we typically do. So this is going to still be length 3 binary strings, and we're going to go ahead and use all 8 of them. And then after we do the gray code, we're going to tie this into the graphs. Okay, so I'm going to start off with the same thing as we did before. We started with 3 zeros, then we had 2 zeros and a 1, and then we had our issue. We couldn't write the one that corresponded with a 2. So what we want to do next is you don't want to repeat any of your strings more than once. That's not allowed in a gray code. But you want to, the next string that we use for 3 digits, we want to have only one of the digits change. Now if you change the third position here, it'll go back to somebody you already used, so we don't want to worry about that. So let me do check marks on the ones we've used. Okay. But what we can do is we can change either of the zeros to 1. And it doesn't matter which one you change to zeros, which one of those zeros you change to 1, but I'm going to go ahead and change the middle one to a 1 just because that's what I would think to do. Okay, so if we go back to our list of binary strings that we had earlier, this guy here would be going corresponding to 3, and I'm just going to check it off so we make sure we get them all. Okay, so the next thing that we would do is we would say, all right, well, we need to go ahead and we need to change one of these 3 digits to the opposite. We could totally change the 0 to a 1. That's fair game. If we change the middle one back to a 0, that goes back to somebody we already have, so we don't want to do that. But I'm actually going to change the last digit to a 0. Okay, and that actually picks up the 2 we had missed before. Now, next thing that we want to do is we want to go ahead and switch out one of these digits. If we switch out the middle digit, it's somebody we've already had. If we switch out the last digit, somebody we already had. So the only place we can go now is switching out that first digit to a 1. And that turns out to be one of the numbers over here, 4 through 7. That turns out to actually be 6. Okay. Now, we can't switch this first digit back to a 1 back to a 0, because if we did, we'd pick up all of the 4 strings that started with 0. We've already used all of them. So that guy has to stay a 1. So we can only switch out the last 2 positions, either the middle one to a 0 or the last one to a 1. And I'll go ahead and just switch out the last one to a 1. Okay. So that picks up our 7. So we've got 2 left to do. Now, notice the 2 that are left. So we're currently here at 7. We can either go to 5 or to 4, but notice if we try to go directly to 4, that would be changing both of these guys over to zeros. That's 2 moves at once. You're not allowed to do it. So we're going to have to do 5 and then 4 in that order. Okay. So the next one here would be 1, 0, 1. That just switches the middle digit to 0, and the last one would be 1, 0, 0, and that takes us all the way through the entire string. Now, something that I did here, just because it's what I normally do with grade codes, but is not a requirement of grade codes, is notice this very last one down here and the very, very first grade code, they actually also differ by exactly 1 digit. And what that allows you to do is it almost if we're talking about graph stuff, that converts this essentially into a cycle where the next one down could have looped back to the very top one. Now, in the actual official definition of a grade code, it's not normally defined that way. So if we had chosen different options when we had different options through here, maybe we would have ended up with something like 1, 0, 1, and that one would not be one digit different than the first one, and that's still okay for the grade code. Okay. All right, so let us now pop this into graphs. Okay, so if you're looking at a grade code, this is always going to be applicable to some sort of n cube, otherwise known as a hypercube. Okay, so we're going to look at a 3 cube. Why? Because we have like 3 binary strings, and a 3 cube can be represented in a bunch of different ways. For the ones that are a 1 cube, a 2 cube, or a 3 cube, I like to write them so that they draw them so they actually look like cubes. But you don't have to, and I'll show you both ways. So this one here, I'm going to try to make this guy look like an actual cube. Ba-doop. And then straight down. And we've actually looked at this guy before. I believe when we looked at it before, it was actually a directed graph. Okay. Now, here's the relationship between the graphs and the binary strings. You're looking at your binary strings. Here are going to be the labels on your vertices. Now, here's how you label. Maybe this on the bottom corner here, this one is 0, 0, 0. Everybody who's adjacent to 0, 0, 0 has to differ from 0, 0, 0 by exactly 1 digit. So, for example, on this bottom level that was trying to look like a square and I butchered it, maybe over here you have 0, 0, 1. Now going in the back, this one, maybe that's 0, 1, 0. So notice they have only 1, 1. And if we go up, maybe that's 1, 0, 0. Okay. Now, if we look at this back corner here, it's got to differ from both of these two by 1 digit, so that because it's adjacent to both of them. So notice the only way to differ from both of those two binary strings by 1 digit is 0, 1, 1. So notice here, the middle 0 converted to a 1, and here the last 0 converted to a 1. Now, going up, this guy here, to differ by 1 digit, somebody label that we haven't used yet, on the upper level would be 1, 1, 1. Okay. Now, if we do that same thing for these guys here in the back, if we go up, it needs to differ by 1 digit, and the only 1 digit that hasn't been changed yet is if we change the first 0 to a 1. So this would be 1, 1, 0. Quick check to make sure that differs by 1 digit for the ones it's supposed to be adjacent to on the top level. Yes, that 0 turned to a 1, and yes, the middle 1 turned into a 0. Last guy should be the only 3-digit binary string that we haven't used yet, so this should be 1, 0, 1. Notice it differs from this guy down here by 1 digit, differs from that one by the middle digit, differs from this one by the last digit. Okay. Now, the gray code. Let me follow in order the gray code. Okay. So we started with our gray code at 3 zeros, so starting right here. Then we went to 0, 0, 1. Then we went to 0, 1, 1. Then we went to 0, 1, 0. Then we went to 1, 1, 0. Then we went to 1, 1, 1. Then we went to 1, 0, 1. And then we went to 1, 0, 0. I'm going to give a pause here. Look to see what you think that represents in the graph. All right, so what do you see? What happened? This gray code, if you followed how we found it, did what? It actually traveled and hit every single vertex in the graph, in this hypercube graph, or this n cube, in this case a 3 cube. What happened? It visited all the vertices exactly once. A gray code 100% corresponds to a Hamilton cycle. So, a Hamilton, any Hamilton cycle, or as your book calls it, Hamilton circuit, and this is in and n cube, this corresponds to a gray code. Specifically a gray code on those binary strings. Now, to get that translation, you do have to go ahead and label all of your vertices in the way we talked about, where adjacent vertices were binary strings that differed by exactly one digit. And notice then that's why any Hamilton circuit is going to correspond to a gray code, because just following the edge does that same one digit change that we talked about in the gray code. Okay. Now, this guy here also, and I talked about how it could be drawn in several different ways. This guy can also be drawn so that it looks like this, because this is actually a planar graph. The larger n cubes, not so much, but at least the smaller ones up to n equals 3 are planar. Okay. And you could have done the exact same thing when you didn't have all the lines crossing as well. Okay. But that would be the tie-in between gray codes and the Hamilton circuits.